Okay, so today we're going to be talking about variants of induction. So first of all, we're going to be talking about induction from a starting point, and this is covered in Logic and Proof, Chapter 17, Section 2. So make sure that you read that before you listen to this video. All right, so the principle of induction from a starting point, as I've written it out here, is very similar to the normal principle of induction. It just might be true sometimes that not all the natural numbers have a certain property, but all of them after some number like 2 or 5. So we can use a very slight variation of the principle of induction to prove such a predicate. So say we want to prove that some predicate, so we've got some predicate here, and say we want to prove that the predicate holds for all n greater than or equal to some specific natural number m, like 2 or 5. So we've got this predicate and we've got the natural number in mind. Then if we can show, first of all, that p of m holds, so not p of 0, but now p of m, which is our new first guy that we're interested in. And if we can also show that if p of n holds, not for any n, but for any n greater than or equal to our new starting point, then p of n plus 1 holds. If we can show these two things, 1 and 2, then we can conclude that p of n holds for all n greater than or equal to m. Okay, so just a slight variation. And let's look at an example where we should use this principle of induction and not the normal one. So let's consider the predicate p of n to be n is strictly greater than, n squared is strictly greater than n. So this is of course not true for 0 because 0 squared is equal to 0. It's not true for 1 because 1 squared is equal to 1. But it is true for 2 because 2 squared is greater than 2. And we should of course expect that it's true for all the natural numbers greater than or equal to 2. So we want to show that p of n holds for all n greater or equal to 2. Actually, let me write here, not n, but m, so that looks more like the principle of induction that we've written down. Okay, so here's how a proof would go. So just as before, we want to tell the reader what's going on. So we're just going to tell the reader that we're doing induction, and so our proof will have a very particular pattern, which is first we're going to show the base case and then the inductive step, and so they know what's going on. Okay, so we proceed by induction on n, and first we show the base case. Okay, and what's the base case? So we want to start at 2. We want this should be n. Let me just write n there. And m is 2. That's what I want to say. So m is 2. So we want to show our statement for m equals 2. And so what will that be? That will be that m squared is greater than m, but m in our case is 2. Okay, so we want to show that 2 squared is greater than 2, and we won't do any work in this proof. I think it's enough just to cite elementary school. So since 2 squared equals 4, and 4 is greater than 2, this holds. I think that's certainly enough to say. Okay, so now we want to show the inductive step. So let's suppose that n squared is greater than n for some n, well, say some natural number n greater than or equal to 2. Now we want to show that n plus 1 squared is greater than n plus 1. We want to show this predicate p of n plus 1, and that's what it says. So we can just do some calculation. So let's look at the guy on the left-hand side. I think it's a reasonable strategy, even if you didn't know where you were going, to say, okay, let's multiply out this guy to see if we can get anything from that. So we know these two things are equal. And now, since we're supposing that n squared is greater than n, we know for a fact that this guy is greater than, well, here we could put n plus 2n plus 1, and this is 3n plus 1. And now we want to say eventually that all of this is greater than n plus 1. Maybe there's some work here to do, but I think it's quite clear. We can say, actually just in one step, that this is true since 2n is greater than 0 because n is greater than 0. So since n is greater than 0, 2n is greater than 0, so 3n plus 1 must be greater than n plus 1. Okay, and let's also put a little hint here why this is true, why this step here is true, which is that we've used the inductive hypothesis. Okay, so there's our proof. We just did this calculation. We used our inductive hypothesis once to replace this guy by n, putting here greater than sign, and otherwise the calculation just involved elementary school arithmetic, and then we find what we want, which is that this guy is greater than this guy. Okay, so our inductive step is over, and we could say at the end of this paragraph, thus we've chosen the inductive step, but I think it's enough to just sum up the whole proof and say, thus by the principle of induction, we find that n squared is greater than n for n greater or equal to 2. All right, and there's our proof.